Welcome students. So till date we have discussed about the 8051 microcontrollers architecture, its various addressing modes and the instruction sets, followed by discussions on developing small assembly language programs in order to solve some simple logic issues ascending order or sorting the given arrays in ascending or descending order, etc. Now let's look into the next section in which the programmers are more involved, where we will be discussing in detail about the internal peripheral programming. So in this session we will be discussing about what are the different peripherals that are available in 8051 microcontroller, how it can be made into access by a programmer, what are the special function registers required, and what are the peculiarities of each of the registers, and what are the steps required for realizing each of the functions that can be realized using the various peripherals that is available in our 8051 microcontroller. So to begin with the discussion, we start the discussion on peripheral programming with the timer module. So in 8051 microcontroller, we to have two 16-bit timers or counters, which is designated as or nomenclatured as timer 0 T0 and timer 1 T1. So 16-bit timer means this timer or counter module is capable to count value from 0000 H to FFFFH. Okay, so and this counting from 0000 to FFH takes place at every clock pulse that reaches this timer module, and the clock frequency at which the timer operates in general is defined by the oscillator frequency divided by 12. We will be looking into that designing of the clock frequency, etc., in detail in the coming sessions. Now the other feature of the timer module that is available in 8051 microcontroller is that you can program the timer to count from the values from the initial value to the final value, that is FFFFH, based on the internal clock pulse that is available inside the 8051 microcontroller, or we do have an external pin. T0 and T1 is a name of those pins, and depending upon the transition of 0 and 1 logic on these pin, we can program the timer to count from the initial value. So there are two options: either you can use the internal clock pulse, or else you can use the signals or the logic level, that is the transition between the logic levels that occurs at the external pin, that is T0 and T1, designated on the 8051 microcontroller chip. Okay, and if you look to the functions, generally we make use of this timer or counter module in order to count the machine cycles and to provide a specified time delay in our program, or in implementing or in solving some specific problems. Apart from that, we can make use of these timers or counters in order to calculate the time delay between two events, in order to count the number of events that occurs. Then you can use the same timer and counter module in order to generate the baud rate or the clock signal that is necessary for the serial port or for the serial communication module, that is UART, that is present in the 8051. And the same timer and counter can also be used for pulse width measurement as well as frequency measurement. So this is the overall picture about the timer and counter module. That is, apart from the measurement or implementing some time delay, we can make use of many other applications, make the use of timers for realizing many other applications, and the operation of the timer can be controlled by either using the internal clock pulse or by using the external signal from the external pin, that is T0 and T1. And the size of the counter or the timer that is available in 8051 is 16-bit. Okay, now let's move on to the SFR, that is a special function registers related to our timer module. So the first set of special function registers is known as the timer count registers, and as we told, we have two 16-bit timer corresponding to timer 1. We have the register TH1 and TL1, where TH1 stores the upper 8 bits and TL1 stores the lower 8 bit count values of related to the timer 1 module, and TH0 stores the upper 8 bits and TL0 stores the lower 8 bits corresponding to the timer module T0. Okay, and the count value that is stored inside these count registers is taken as the initial value, and at every clock pulse that reaches to this timer module, it gets incremented and it goes up to FH. And once the overflow from FH to 0000H occurs, then the timer module generates an interrupt, or it sets a timer interrupt flag indicating that the count has been reached. Okay, so this counting rate from the initial value to the maximum overflow count, that is FFH, takes place with respect to the signal frequency, which is in most of the cases it takes place with respect to the signal frequency produced by the internal clock, and it is equal to the oscillator frequency divided by 12. So in general we make use of the crystal oscillators on 8051, and it will be having a value 11.0592 megahertz. Okay, so the oscillator frequency will be 11.0592 megahertz divided by 12. So that is the equivalent frequency, that is 921.68 kilohertz will be the counting frequency. Okay, so it will be the frequency of the counting signal that is applied to the timer to increment the count in the count registers that is being used. Okay, now the next special function register related to our timer module is the T mode register, or the timer mode control register. So from the name itself, we know that it is the set of, it's an 8-bit register, special function 8-bit register associated with the timer, which is used in order to control the mode of operation of the timer. So here you can see that actually this 8-bit register uh, contains, or it associates with both the timer 0 and timer 1. The lower 4 bits corresponds to the timer 0 and upper 4 bits corresponds to timer 1, and we can see that the upper 4 bits is the replica of the lower 4 bits. So in this we have the M1 and M0, these are the mode select bits. So with respect to the value that is assigned to each of these bits M1 and M0, we can decide in which mode does our timer needs to work. So if I am setting the value of T1 and D0, then the mode of the timer 0 is being configured, and if I am setting the value of D5 and D4, then the mode of timer 1 is being set. Then we have the next signal, that is C bar T bar. So this is a pin, or this is a bit present in this particular register, which takes care of designating whether the timer module available in our 8051 microcontroller needs to act as a timer or as a counter. So if we apply the value C bar T bar equal to 0, then the timer module works as a normal timer and it implements some delay. And if I need to implement the counter functionality in our 8051, then I need to configure C bar T bar equal to 1. Okay, so if I am setting D2 bit as 1, then timer 0 acts as a counter, and if I am setting the D6th bit of this register, then the timer 1 will be configured to act as a counter. So by default the value of C bar T bar will be equal to 0, so that the timer 0 and timer 1 can be used as a general purpose timer used for implementing some delay. Now we have one more bit, that is the gate bit corresponding to D3 and D7. So the gate bit in D3 corresponds to timer 0 and gate bit in D7 corresponds to timer 1. So this is a bit which gates the clock signal at which the timer keeps on counting. So by default it will be equal to 0. That means the timer will be incremented. The count value that is stored in the timer count register will be incremented with respect to the internal clock frequency. And if I am setting the gate bit, that is D3 or D7 equal to 1, then the corresponding timer time counter register will be incremented with respect to the external signal. Okay, with respect to the external signal that is received through the interrupt pin. Okay, so in that case, the logic state transition from 1 to 0 that occurs on the interrupt 0 and interrupt 1 will be taken as the clocking signal for the timer counter register to increment its count from the initial value stored. So this is the same thing which I have already explained. The textual explanation of what I have already said right now. So we will be looking into the mode of operation in detail. So if you look in a simple glance, you can see that if I am configuring M0 and M1 equal to 0, then the operating mode of the timer is 0, mode 0, and the peculiarity of this particular mode is that then the timer is now acting as a 13-bit timer mode. That is, it can count from 0000H to 01 not 01 1 f of h. Okay, that is a 13 bits can be used, and in this out of this 13 bits, the lower 8 bits will be stored in the thx registers, and the upper 5 bits of this of the count will be stored in the tlx register. Okay, and this upper 5 bits which is stored in the tlx register act as a prescaler in order to decrement or prescaler to divide the counting frequency. Okay, so by default we'll be having the counting frequency as oscillator frequency divided by 12. So this frequency will be further reduced by the factor 32, or based upon the value that is stored in the 5-bit value that is stored in the TLX register. Then if we are configuring M1 equal to 0 and M0 equal to 1, then we will be moving into the mode 1, which is a 16-bit timer module. That means the timer can count from 0000H to FFFFH. And we have M1 equal to 1 and M0 equal to 0, which makes mode 0. So in this case, the timer 0 and timer 1 can be, if you're configuring both the timer 0 and timer 1 in mode 3, both of them can act as an 8-bit auto reload timer or counter module. That means in the other cases, whether if you go for M0, mode 0, mode 1 or mode 4, once the overflow from the maximum value occurs, then in order to reload the initial value again, we need to perform a software instruction execution. Okay, but in mode 3 there is no need of an additional or a specific software instruction for reloading this value. It will be automatically reloaded. Okay, so that is the peculiarity of mode 3. So it acts as an 8-bit format. So the corresponding THX register will be holding the copy of the initial value, and the TLX register will be automatically reloaded with this value that is stored in the THX register, and based upon the clock signal, the TLX register will be incremented and the overflow will be occurred once it reaches FF h. Okay, then we have the M1 equal to 1 and M0 equal to 1, that is 1 1, that is mode 4, which is normally designated as the split timer module, in which the timer 0 itself can be used as two separate 8-bit timer module. And the peculiarity of this particular mode is that only one timer can be used specifically. The other timer has to be used for some other purposes other than implementing delay time. Okay, so in general, if in any of the applications, if we need to make use of this configuration, that is mode 4 configuration, then we will be preferring timer 0 to operate in the mode 0 configuration, and timer 1 will be used generally for the baud rate generator in that case. Okay, then the next register which is concerned with the operation, or in order to enable the functionality of the timer peripheral, is the timer control register designated as TCON. And of this 8-bit register, the upper 4 bits only the upper 4 bits is associated with the operation of the timer. Okay, so as from the name of the register timer control, the upper 4 bits of this special function 8-bit register is used for controlling the various operation of the timer. So we have TF1 and TR1 and TF0 and TR0. Okay, so TF1 and TF0 are the timer overflow flag. So these two flags indicates the status of overflow that occurs in the timer modules. So for example, if we configure timer 1 as a 16-bit timer, that is in mode 1, then when there is an overflow, that is when the count reaches f of h, and in the next clock pulse it will be initialized to 0000h. Okay, so this transition of the timer counter register from FFFFH to 0000h, that is from the maximum value to the initialized value on the occurrence of a clock pulse, is considered to be the overflow situation. Okay, so once we turn on the or we start the timer, once this overflow situation occurs, then it is been indicated by setting the value of these bits TF1 and TF0. So TF1 corresponds to the overflow flag of timer 1 and TF0 corresponds to the overflow flag of timer 0. And we have TR1 and TR0, which is the bit that corresponds to the bit that can be used for starting the timer. So if I make a software uh, in instruction to make the values of this bit as 1 or to set the values of this bit as 1, then it helps in turning on the or enabling the timer to start count. Okay, so a software writing, that is software instruction to make tr equal to 1 is required to turn on the timer and start the counting process. Similarly, for timer 0, we need to make tr0 equal to 1. Okay, so the same thing has been described here. So the upper 4 bits only is only used for the control of the timer, and the lower 4 bits of this register is generally used in the interrupt case. So we will be discussing those bits in detail while we discuss the interrupt programming in 8051. Okay, now let's discuss in detail about the modes of operation. So as we have seen, by default we have the oscillator, and it has been divided. The oscillator frequency is divided by 12, and that frequency is clocked to the timer counter through a control bit. Okay, so this control bit can be is being controlled, or this control switch is controlled by the value of the gate bit which is present in the T mode register. Okay, and as we know that this counter register can increment based on the signal either from the inner clock pulse when it is configured to act as a timer. Also the same count can be incremented in the case of a counter operation also. Okay, so when c bar t bar equal to 0, then the internal frequency is taken by default, and based on the control switch status, okay, either it will be switched directly, or instead of this, even though if you are making c bar t bar equal to 0, depending upon the gate bit, the external signal can be used to enable the counting. When we go for the counter operation, we will be making c bar t bar equal to 1, so that the external signal, the signal that is coming from the T0 or T1 pin, will be bypassed by the control circuit or the control switch to the counter register for incrementing. Okay, so here you can see that there's a 13-bit timer, so we have 13 bits. So of this 13 bit, the lower 8 bits are stored in THX, and the upper 5 bits of the count is stored in the TLX register, and this 5 bits which is available in the TLX is going to divide this signal further. Okay, so when we go for the internal frequency, the initial clock frequency, that is which is divided by 12, is further divided by 12. So in effect, the signal the frequency of the signal which enables the count value in THX to increment will be oscillator frequency divided by 12 into 32. That is, if I am having 5 bits together, 2 raised to 32, 2 raised to 5, 32. Okay, so 12 into 32, that is 384 times. So the oscillator frequency is reduced by 384 times, and that frequency is used for incrementing the count that is stored in the THX register in this. Okay, and once it increments and reaches FFH, and the next clock pulse, it will be initialized to 00H, and at that instant the corresponding timer overflow flag will be set, and which can be used for generating an interrupt or some other purposes based upon the programming topology that is being used. Okay, then so it is there. So if you look in total, from the initial value loaded, the maximum machine cycle or maximum time period that is required uh, to make the registers Okay, we have the register THX and TLX that equal to 0 will be 8192 machine cycles in this case, that is 2 raised to 13. Okay, so that much times it is required. Now if you go for the timer 1 module, so here the basic block diagram is same, but here you can see that the control bit has been expanded, or the control switch has been expanded and shown either through TR1 or the gate signal, etc. So this is because this is the most commonly used mode. Okay, that's only the reason. If you are avoiding this, it's not an issue. Okay, basically. So based upon the C bar T bar signal, either the timer can act as an timer or an counters module, and based on the gate value, the either the signal from the external source, that is through the interrupt pin, or from the, or based upon the signal, that is the timer start signal TR1, the signal will be reaching the counter register. So here both the registers will be acting as a full counter, that is both we can count from 00 to FFH. So total 16 bits 0000H to FFH will be enabled, and on occurrence of the overflow from FFH to 0000H, then the timer overflow flag will be set. Okay, so here the maximum count is from 00 to 65,535. So the maximum delay that is possible in mode 1 is 65,536. Okay, that's that much units is the maximum delay that is possible here. Okay, now we go for the mode 2. As I told, mode 2 is the mode of operation of the timer in which we have the auto reload feature. So the initial count value which has to be loaded to the counter register is stored. It's an 8-bit value, and it will be stored in THX register, and the copy of this value will be loaded to TLX register, and based upon the most probably, and this mode 2 operation is only used in timer configuration. We are not using this mode of operation counter operation in general. So in this block diagram you can see that the timer module in mode 2 is only working for the timer operation. Okay, so based upon the timer start bit, that is TRX, that is TR0 or TR1, the internal clock frequency will be bypassed to the TLX register, and it keeps on counting, and on the occurrence of overflow, that is from FFH to 00, the timer flag will be set, and automatically this overflow is indicated to switch or to enable the copying of the value that is loaded in THX register automatically to TLX register. Okay, so that is the mode of operation of the timer modules in mode 2. So here the maximum value that we are possible is from 00 to FFH, that is 256 count values can be obtained in this case. Okay, so here we need not load the value to the counter register deliberately, but we need to clear the timer overflow flag using some software codes. Okay, sorry. Now we have the timer mode 3. So this is the last mode of operation that is supported by the timer modules. So as I told in the earlier stage, in most of the cases we will be making use of the timer 0 alone to operate in the mode 3. Okay, in most of the applications if needed. So in this case the timer 0 will be acting as two separate 8-bit timers. So here you can see that the timer clock, that is by default Indian clock frequency, that is oscillator frequency divided by 12, is supplied to TL0 and TH0. So these two are the count registers for the two 8-bit registers, and here you can see that if an overflow from FFH to 00H occurs due to the increment in TL0 register, the corresponding overflow flag is TF0, and for the overflow that occurs due to the on the count of TH0 register, the overflow is detected or indicated using the overflow flag of timer 1. Okay, so that means now the timer 0 is using its counter register to implement two separate 8-bit registers, and their overflow statuses are indicated by using two flags. As we know, only there is only one flag for the timer. So here the timer 0 is borrowing the overflow flag from the timer 1. Okay, so that is why we say that during this mode of operation, if we make use of timer 0 to operate in mode 3, then timer 1 cannot be used in any timer for any timing operations. That is, since it is not having its overflow flag, we cannot make use of its timer registers. Okay, the overflow of its timer registers to implement some timing informations in our program. Okay, so that is about the mode 3 of operation. This is the rare of rarest mode that is being used in timer. Okay, so now if you look to the basic operation, timer operation, this is a basic operation. We will be loading the initial value to the counter register. So here you have the pictorial representation of the operation of the timer, which is configured, the timer 0, which is configured in mode 1. So we have a 16-bit value which can be loaded to the timer counter register. So that value is now available in TH0 and TL0. So if initially I am loading the value FFC. Okay, FFFC is a initial value. Now on making the timer, to enable the timer, I need to make the bit TR0 as 1. So when I am applying TR0 equal to 1, then on the occurrence of the first clock signal, this count will be incremented to TFFFD. Okay, on the next clock signal it will be shifted to, or it will be incremented to FFFFE, and on next clock pulse it will be incremented to FFFF. Okay, and on the next clock pulse you can see it is been initialized to 0000. Okay, so on this overflow from FFFF to 000, you can see that the timer's overflow flag will be set as 1. Okay, in all other cases it will be equal to 0. Okay, at this time you need to stop the timer. Okay, so what we will be doing in the program is that we will be initially setting the mode of operation. After that we will be loading the corresponding count value to the count register of the corresponding timer which we are going to use, and after that we will be turning on the timer by making the corresponding TRX bit as 1, and then we will be monitoring the status of the timer overflow flag, that is TFX. Okay, TF0, TF1, and when it is equal to 1 we will be stopping the timer, as well as we will be doing the action corresponding to that particular delay. Okay, so here you can see that after this value is been loaded, on starting the timer, first one clock pulse, second clock pulse, third clock pulse, and fourth. Okay, so ineffectively there is a delay of 3 clock pulses. Okay, so there is a delay of 3 clock pulse, and this delay 3 clock pulse means the delay of 1 clock pulse is determined by inverse of oscillator frequency divided by 12. Okay, so that is the by default operating frequency. So if you look to the maximum delay that is achievable in each of the modes of operation, you can see in timer in mode 0 the maximum delay is 12 into 32, that is the initial pre-scaling. So by default the initial frequency, okay, the oscillator frequency is divided by 12 alone, but in case of mode 0, the 5-bit value present in TLX register is also going to provide a pre-scaling operation. So 12 into 32 times, okay, so 12 into 32 means 384 times. The final value is 256, and the initial value is the value that you are going to load to the THX register. Okay, so 12 into 32, that is 382 times 256 minus initial value by frequency, will be the maximum delay that I can achieve in mode 0. Okay, and if you go for mode 1, we know that it is a 16-bit timer, so the maximum count value is 0 to 65,535, that is 65,536 values. So the time delay occurred is achievable is 12 into 65,536 minus the initial value that is loaded to the counter register divided by frequency, oscillative frequency. Okay, and for timer mode 2 and 3 we only have an 8-bit timer, so the maximum time delay is equal to 12 into 256 minus the initial value, the initial 8-bit value that you are loading to the count registers, the whole divided by frequency. Okay, so we will be getting more clarity. Okay, you will be getting more clarity and more definition about how this time delay is being calculated, etc., while we go for the programming session, or while we practice the programming of timer. Okay, so that's all about the timer module of 8051. So here we have looked upon into the basic features of the timer modules available in 8051, their applications, and the various special function registers associated with configuring the timer module in 8051, and the modes of operations through which the timer modules can be taken through, and the maximum delay that is possible in each modes of operation of the timer. Okay, so that's all for today. In the next session, we will be discussing about the details of the interrupts. Okay, the feature interrupts that is available in our 8051 microcontroller. Thank you.